can start.
All right. Thank you so much for the kind introduction. I must say that was very flattering. And please don't call me sir. I'm not that old yet. I'm a 2017 pass out. So just greeting me as Sayak by my first name is just fine. Whenever someone calls me sir, I feel very old enough, and I don't think I'm a teacher yet. So, but yeah, that was very kind of you. Now, without wasting anyone's time anymore, let me get straight to it, and let me start by sharing my screen. Uh, yeah, it should be visible, I hope.
Yes, it is.
Yep, cool. And just as a disclaimer, so a storm is heading toward where I live in. So if I get disconnected, be noted that it will be because of that. So yeah, that was the disclaimer. And yeah, now the computer vision, especially from the context of deep learning, is a ghastly vast area, and I am no way in a place to share all the achievements that have been done in 2021. So please do not mistake this as a sort of a comprehensive list of all the trends that have been going on in computer vision, especially from the context of deep learning. But I can only speak for myself and the kind of experiences that I have gathered over the months in 2021. So I just wanted to get that out before we start. A bit about myself, sort of unapologetically reintroducing myself. I'm a machine learning engineer at Carted. I get to train very deep neural networks on large scale image recognition problems like fine grained image classification, localization, and so on. But besides that, I also get to work on MLOps related things in order to make these things work at scale. So I have a flair for open source. Of the work I like to contribute to TensorFlow Hub, Keras examples, neural structural learning, and also some of the research repositories maintained by the Google research team. Now, when I really do not have anything to work on, I like to watch things on Netflix or any other OTT platform for that matter. And everything that I'm going to be talking about are all available at this URL, sayak.dev. And along with that, you will get all of my coordinates like email, GitHub account, and so on. But feel free to stop me at any point in time if you think anything is unclear. This session is meant to be really an interactive session. So don't wait for the talk to end and then ask your question. Feel free to interrupt me at any point in time and ask it away anyway. So yeah, I wanted to talk about the objectives of this work. At least this is the way I see it. So first and foremost, I really wanted to help you folks discover what might be more interesting to work on in the coming days, and maybe help you a bit in deriving your next project idea. Because if you are dabbling in ML or computer vision or NLP or anything like that, for that matter, it's really hard. It must be hard for you to come up with a unique project idea that might shine well on your resumes or even curriculum vitae. So I have been there. I'm still I still go through that phase sometimes. So I hope you can take some project ideas from what we are going to discuss for the 30 minutes or so. Also, another objective is to help you get up to speed with some of the cutting edge stuff happening in this area. Again, this is in no way an exhaustive and a my experience and the club to do and also do as a part of my work. So yeah, please take that as a very strong and strict disclaimer. Now, the first trend I would like to really discuss is resource efficient models in the age of models like GPT-3, Megatron, DALI, where the number of parameters seem to be blowing up and blowing up. It's also important for us to take a step back and think about how can we use these models on resource constraint environments where internet accessibility might not be a well assumption. Now, starting off, as I mentioned, state-of-the-art models are often very hard to run offline on tiny devices such as mobile phones, Raspberry Pis, and other microprocessors. Now, if you are following the trend with different IoT-related devices, or even with the intelligent tabs that we get in our mobile phones these days, they often do not require any internet connection or so on, but they still incorporate some sense of intelligence or some sense of automation in a very clever way. Now, I think we as practitioners, it's down to us to wonder how these things are being made possible. So with this, for the next 5 minutes at least, I want to be able to provide a very brief introduction into that sneak peek as to what happens when we open up Google Photos and see all of our faces getting clustered into a single region. So moreover, heavier models. So again, coming on that point, we are not going to be talking about the system architecture design of Google Photos, but at least some of the tooling behind it as to what makes those heavy model portable on tiny mobile phones, even when they are not making any cloud requests, and how they are kind of operating without having access to internet in the first place. Moreover, of course, heavier models tend to have significant latency. The more complex your network architecture is, chances are likely that it's going to be introducing significant amount of inference delay. And in mission critical and battle ready applications, oftentimes we cannot really afford that slow inference speed. And heavier models can affect your infrastructure costs significantly. Now, taking a simple example rather, consider deploying and maintaining a model that weighs about 500 GBs as opposed to maintaining a model in production that is only about, let's say, a GB, right? You can immediately imagine the kind of hurdles that one would have to sort of go through when dealing with such a compact and dense infrastructure in order to sort of pull up a 500 GB model. So it's anyway always a good practice to try to think of ways to optimize your end model that would go for production. And it's a legit thing to do whenever, even when we are operating with cloud APIs, such as the vision APIs or the speech APIs offered by any cloud service providers for that matter. And another question would be, what if cloud-based model hosting is not an option? What if your application stakeholders require you to design applications so that they can work without having any network connectivity? And also, what if you have a stringent requirement that suggests that user data must not leave the mobile phones or any other devices for that matter? So in order to cater to those conditions, it's really important for us to think of ways so that we can directly put a machine learning model inside an application and make it work as seamlessly as possible. Any questions? I saw glitch. Nice.
Yeah. So like you said, like heavy models can affect the infrastructure. So is it like we should start with a light architecture from the start, or like you would like go for a model that can actually act properly and then go for pruning later on, or like go for int 8 instead of float 16 later on? So like what should be the first approach towards the problem?
Excellent question, I would say. So see, one of the golden rules, in my opinion, at least in machine learning, is to always start with a baseline. If your fancy convolutional neural network cannot beat a random cannot beat a random chance, then it's no better, right? So it's always a good practice to sort of disclose complexity in a progressive manner. Maybe start with the simplest model first, see how it's performing on your dataset, and then slowly start adding complexity. Now, of course, if there's sufficient literature available for the problem that you are solving, and if all of them are suggesting that, hey, bigger models always tend to perform better for this particular tasks, then yeah, be my guest. Feel free to try from there only, but it's always a good practice to sort of take a step back and see if simpler models are working already well. So this is one part, but coming to your other questions, I think I have a little bit more to discuss on these things. And as we proceed with the rest of the presentation, hopefully those things will be clear. Does that work?
Yeah, sure. Thank you.
Okay, cool, cool. Now, one of the solutions to the problems we just discussed is sparse training of neural networks. So the motivation here is, what if we can train very small neural networks in the first place? What if we do not need to train bigger networks and then prune our way toward our smaller network, or any other techniques for that matter? Knowledge distillation, for example, requires you to train a well-performing bigger network, and then only you can distill all of that knowledge into smaller networks and so on. But what if we can get away with smaller networks in the first place? And sparse training seems to be providing a principled approach for us to do that. And let's see. So imagine training with matrices having lots of zeros, and I'm mentioning matrices because neural networks are nothing but matrices. So imagine training with matrices having lots of zeros, and zeros because it's very efficient if you wanted to compress a matrix that has lots of zeros, and you would get tremendous benefits if you wanted to take that compressed version of your sparse matrix and put that inside an application, and you would get tremendous space related benefits. Now, why zeros? Introducing lots of zeros because not all the dimensions in a high dimensional sphere are interacting with others in the same manner, and neural networks tend to shine exceptionally well when it's being fed with high dimensional data like images, videos, speech and text data and so on. And when we are having to deal with such high and large dimensions, not all the individual dimensions are sort of interacting with each other in equal manners. So zeroing some of them out might be a clever thing to do. Now, performance, of course, might take a hit because you are eliminating some of those redundancy, but neuroscience also suggests that having some amount of redundancy is needed in order to help you learn something in a better manner. And this is directly coming from neuroscience and all the brain stuff. But yeah, as I mentioned, performance might take a hit if we introduce lots of zeros, but there has to be a major reduction in the number of multiplications, and that will lead you to sort of have some amount of convergence, but within a drastically reduced time frame. And of course, this will eventually lead to decrease in the overall training costs and so on. And here's a visualization of how sparse matrices look like. We are starting with a dense kernel taken from a shallow neural network, and gradually we are incorporating sparsity. And as you can see, at 99% sparsity, there are literally some points in the space, like the stars we see in the night sky. So this is roughly the idea, and there has been a lot of improvements in this area. And it's still very nascent. I haven't yet seen many folks doing sparse training of neural networks, at least for production related models, but it's definitely an interesting, or rather a practical direction in research that you might expect to see a lot of papers on across many below a certain threshold. At least this is the most basic form of pruning, where you discard, where you
Sayak,
yeah, go ahead.
yeah, sorry. Like, we lost you for 5 seconds there. Can you please like
Of
go?
course. Yeah, okay, sure. So I was mentioning that one closely related technique to sparse training is pruning, as our dear host was mentioning, pruning. So in pruning, you discard network parameters that are below a certain threshold. At least this is the most basic form of pruning, I would say, and popularly known as magnitude-based pruning. And it's applicable to any neural network that you can think of, whether it's a vanilla recurrent neural network, whether it's a pure old multi-layer perceptron, whether it's a convolutional neural network, anything. So the basic idea is extremely simple. So you iterate through all the network parameters and you compare that to a pre-specified threshold, and the parameters where the magnitude is below that threshold, you set it to 0. And again, why 0? Because yeah, we need to go take few steps back, because neural networks are nothing but a collection of matrices, and when there are lots of zeros inside a matrix, it's highly efficient in terms of compression, and it can lead to drastic improvements in spaces and memory requirements and so on. So that was a very brief idea about pruning, and I have also mentioned some good reads about pruning if this sounds very interesting to you. And definitely read about lottery ticket hypothesis if you want to pursue something in the area of pruning or model compression for that matter. And this is how roughly the rest of the session look like. I'm going to be taking some of the examples that might be directly relevant for your research focus or practice, or your focus that is more relevant for practicality of things. And I'm going to be also sort of referring to some of the best resources in that area. So yeah, any questions so far?
Yeah,
Okay,
I think
go ahead.
no.
Go ahead.
Yeah, I
Oh,
guess.
no questions. Cool. Now again, we haven't yet quite left the ground on resource efficient models. There's this simpler technique called model post-training inference, where we tend to take an already trained model and then sort of start our quantization process. Now, typical neural networks typically operate with higher numerical precisions, typically float 32. What if we were able to represent the parameters of that network, parameters and activations of that network in lower precisions? And this should directly result into smaller memory requirements and so on. And by lower precision, I typically refer to floating point 16, integer 8, although there are binary networks as well. But yeah, I'm in this talk, I'm only going to be focusing on floating point 16 and integer 8. And this is roughly the motivation behind quantization. And there's also this another form of neural network training that induces a form of quantization in the training process itself. And the motivation there is to compensate for the information loss that you typically induce during the post-training quantization part. Because when you are reducing the numerical precision to express your neural network activations and parameters, you are snatching away some amount of information from there. And in order to make sure that no information is being lost, what if we could replicate some form of quantization inside the training process itself? And that is exactly what quantization aware training does. And it's also possible to use pruning and quantization in tandem. And I'm going to be leaving you with links that show an end-to-end process of achieving pruning and quantization inside a unified workflow. Sorry, I got a bit distracted. And yeah, here are some good reads. You can read all about post-training quantization from this seminal paper from the Google Brain team. And also, it's now possible to take your TensorFlow or Keras models and train them using the quantization-aware training scheme using the TensorFlow model optimization toolkit. And it's a very faithful toolkit. It's not known to have any security flaws. And I have also used some of the bits from TensorFlow model optimization toolkit in deployment as well. And it seems to be performing pretty well for us so far, at least. Now, another extremely important technique that seems to work extremely well in practice is knowledge distillation. where again the idea is to train a high performing teacher model and then distill its so-called dark knowledge by training another smaller student network to match the labels predicted by the teacher. And that's all there is to knowledge distillation. Of course, there are other formulation of the pre-training tasks and other formulations of the student training setup, but roughly this is the idea. And here are some more good reads for you. The first one would walk you through the end-to-end process of knowledge distillation, the vanilla knowledge distillation workflow introduced by the Google Brain team. I think Geoffrey Hinton was the first author, but yeah. And the second link will walk you through the modern recipes in order to make knowledge distillation work tremendously well. And I think that's it for the resource efficient models. And here are some miscellaneous notes, but again, these are not as important as the other techniques that we just discussed. Again, these are all my opinions. Feel free to form your opinions as well. But I wanted to leave you with another very important direction in research, I would say. And that is when we perform neural architecture search in a hardware aware way. So we explicitly define the search criteria so that it's aware of the kind of hardware where the resultant model will be deployed to. And some examples are mobile date, mobile net v3, of course the mobile net family entirely, regnets, efficient net v2, and so on. And with experience, I must admit that you will learn to combine these different techniques we just discussed. And so far, this following recipe seems to work extremely well in practice. So the idea is train a bigger and high performing teacher model, then perform knowledge distillation and sort of distill all the knowledge of that bigger and high performing teacher model into a smaller student network. And while doing so, preferably use quantization aware training in case you want to deploy your model on mobile devices and so on. And then sort of prune and quantize the distilled model, and you should be able to have a pretty decent model that performs well without you having to trade away with the inference latency part. And here's actually an example that is already deployed at scale, and this deals with deploying speech models on mobile, and the framework is known as Frill. Again, this is from the pioneers of speech recognition at the Google AI team, so feel free to give it a check. And if you are really interested about deploying highly efficient but tiny models on mobile devices or microprocessors and so on, now might be a good time to consider all the information that we just discussed and see what you can make out of them. And also, as a reminder, I'm going to be sharing this deck with you folks. I'll share a link to this deck so that you can refer to it if it's needed. Now, I would like to go to another trend, but before that, I wanted to see if there's any question on the table.
Yeah, I would again go for a question. So like it said like efficient processes for like resource efficient models. Like let's keep aside federated learning. Like let's not go over there. I see there are a lot of architectures, like mobile nets or efficient net, family of mobile nets and efficient nets. But instead of those, like these days, apart, if we also don't like consider transformer based models, if we go for like CNN models, also like people right now also use like VGG and ResNet, like the bulky ones right now also for different research purposes. So like, is that like there is some problem with mobile net that they face? Like let's say they are going for a segmentation model, they still use a VGG or a ResNet encoder for your units for like segmentation. So like yeah, there are in self-driving cars, people are going for a mobile former and sort of architectures that use mobile net, but still there are a lot of areas where people just, I don't know, like is that like there's a hatred kind of thing for like mobile net and efficient net family?
I won't say there's a hatred because this field is still in its nascent stage. People don't like to introduce too much of technical debt later down the pipeline, because it's not just only about the machine learning side of things. There
Yeah.
are other teams into play. And as you may already know, machine learning can be treated as the high interest credit card of technical debt. So maybe that's why, but also as I was mentioning, I have talked to a couple of folks relevant in this industry. They always mention that we still do not have a comprehensive benefit of using these models. At least the benefits are not clear to our teams, and that's why we are reluctant to switch to this fancy models. But I would say, if folks do not try these models, at least in their MVPs, we will never know if this has the potential of being exploited at their fullest scale. The last time I was able to check, EfficientNet family of models were actually deployed across a large set of different Google products. So that might be a good inspiration for other industry practitioners to consider things slightly in a different fashion.
But like, is there any thumb of rule that yeah, here ConvNet would work and you can't use a depth-wise con won't work, like mobile net for or efficient net family won't work? Like, is there any rule of thumb or any
Yeah.
specific area where this fail?
Yeah. So some of the most surprising, not surprising, some of the most irritating cons of depth-wise convolutions are they do not perform I mean, they are computationally, they are way more expensive than regular cons when it comes to hardware accelerators like modern TPUs and modern GPUs. So I mean, in fact, the paper on mobile data actually investigated this, and from there, from their their sole finding was just throwing a bunch of depth-wise convolutional layers do not transfer well when you deploy them using hardware accelerators. And these hardware accelerators also include mobile GPUs in some cases. And in those cases, regular convolutions, when placed in a certain combination, tend to perform not only better, but also faster. So this is one of the hesitations. I would definitely say that networks that have a lot of depth-wise convolutions in their architecture tend to train slower than the networks that have convolutions arranged in a specific manner. And regnets are also an amazing example of that. And regnets are regular convolutional neural networks having regular convolutions, no depth-wise convolutions in the first place, that are faster to train and also are faster in terms of inference latency compared to the mobile net family of networks. Does that make sense?
Yeah, sure.
Now coming to the second trend, let's take a step back and revisit the field of GANs, not GANs, generative deep learning, say, because generative deep learning is not only about GANs. There are also all sorts of autoencoders and other things, but it's definitely not only about GANs. There are diffusion models, NERF, and so on. But yeah, it now would be a good time to consider about how far the field of generative deep learning has come for. Now, this is one of the most common examples, but rather a fascinating example, I would reckon. And generative deep learning has really come a long way. If you take a look into the generative deep learning papers in 2015, you won't be as convinced as you would be today after taking a look into papers like StyleGAN v2 or training GANs with limited data, or even the diffusion model paper and so on. Right now, this is just an example. Now there are other flavors, and if you are really interested to see the extent of image generation, then do visit this website called thispersondoesnotexist.com whenever you are in a crisis of face images, then definitely hit this website and get images like this. And these images were generated from this particular website called thispersondoesnotexist.com. How funny. And there are image generation can come in different flavors. Now I would like to provide a few examples on this, and lots of creative applications, and some are practically quite oriented, I would say. For example, image super resolution. It's practically, I think its importance is paramount. I mean, for all the surveillance related stuff, like drone surveillance that are deployed in wildlife, forest preservation, and so on, image super resolution has to be the number one go-to thing there, because not all the surveillance cameras are high definition, and you cannot really have that sort of extremely large costs that would make your deployment not that friendly for the overall budget that might have been limited allocated for that. And in those cases, image super resolution is definitely one of the saviors there. So image super resolution is one of the most practically oriented applications of generative deep learning, I would say. And there's this another one on domain transfer. We get to see all sorts of applications these days, like PixArt, and so on. And on the left hand side, we see a cartoonizer GAN that can take any natural image and turn it into a plausibly looking cartoonized variant. And on the right hand side, we see the selfie to anime GAN that can take not all images. It tend to perform well on Asian and Southeast Asian faces, but it can take those selfie images and turn it into a plausibly looking anime image. So again, you probably have already imagined this models can fit into mobile applications these days, and you can really get a whole idea of making a creative mobile application with these models. And image extrapolation seems to be another important area here, having lots of applications in things like Adobe Photoshop and photo touch-up, all those kind of applications, where you take in an original image, you mask some of the portions of the image, and then you retouch it with a semantically similar but different portion for the masked out region of the image. So this is known as image extrapolation. And in my opinion, these three things are practically quite oriented and can be used to their fullest extent in real and practical applications. And there's another one, but I would still say it's more on the research side of things, and this deals with utilizing implicit neural representations, like taking all the continuous input signals into consideration, and exploiting the smoothness and the differentiability that's implicitly present in those continuous signals. That is basically the ground for doing research on implicit neural representations, I think. And when you combine implicit neural representations with something like CLIP, you get things like this. Now, believe it or not, this image was generated from this caption, and the caption reads, "Live during a plague." Now, how funny that must be, and how amusing that must be, that we are able to sort of get a quite semantic and plausible, cartoonish kind of an image just from a caption. Now, all these things are being made possible with tools like implicit neural representations and CLIP. And both these works were from different labs. Implicit neural representations were from MIT, if I'm not wrong, and CLIP was by OpenAI. So for more of this stuff, definitely check out this repository called DeepDiz, and I'm sure you all will be amazed. Any questions? Okay, moving on. Yeah, any questions?
No, I think we can move on.
Cool. Now here are some notes and suggestions. At least this is the way how I go about it. So I tend to study these works and implement them whenever possible. And for me, it's totally okay to skip a few parts and focus only on the true novel bits of these works. And as you would see that these works build on top of existing art and then introduce a few different novelties on their own. Now that's why I like to study them, and in order to understand them at a very deeper level, I like to implement them sometimes whenever I get time, and I also feel okay to skip a few parts whenever it's needed. And developing an end-to-end project, like you have implemented, let's say, some architecture, you have trained it well. Now let's say you want to be able to take that model and make something out of it. And developing an end-to-end project can be very, can be, can put you on your edges as far as learning curves are matter, curves are concerned. And this is probably one of the last things that I often do is I try to improve the elements that have been introduced in the work that I'm trying to implement. And one never knows. You may find something novel and make an entire paper out of it, right? But I think it's important to try to also think of ways, or rather find rooms for improvement when you are not getting expected results, I would say. And why you might not get expected results in the first place? Well, that is because you probably have skipped some parts and now you are sort of on your toes to make your implementation work. And believe it or not, improvement ideas can come from there, and it applies to all the other domains, not just machine learning. I'm sure you all have poked with different HTML and CSS templates and have found your way around it. But yeah, this idea of poking around with things and try to improve what you have poked already works. I mean, these hacks are very invaluable to me, and I hope they are to you as well. Now, before I proceed to the next trend, I would like to see if there are any questions.
Okay, so there's a different, like, not mine question. So there's a different question. It says like there are a lot like these GANs, like a lot of GANs like architecture VQ GAN are often associated with clip, and then the results are cherry picked and shown. Like if you implement that same paper, you won't get the results as you have got, so as expected. So is there like any sort of benchmarking the models in generative adversarial networks?
Uh, are you able to see the GitHub repository that I have opened?
Yeah, aiming console. Yeah.
Yeah. This is the official repository of the VQGAN stuff that I just heard.
Yeah.
This repository is pretty reproducible, I would say. If you, again, the work that you mentioned on fusing VQ GANs with clips, I think we do not have a formal paper on that. Folks have sort of come up with these combinations and open source their works in collab. So I'm not yet quite sure how we can benchmark them, because there are no sort of PR reviewed works that we can uh, think through or believe, for that matter. But in those situations, I find that going deeper into the implementations that they are presenting in form of collab or any other GitHub repository is very helpful. And if you are able to immediately spot a bug, maybe open an issue and let the author know that probably some of your results were cherry picked, and this is where I think you might have introduced a flaw mistakenly, and this is how I would fix it. But on an overall basis though, that combination of using VQ GANs or DALI, for that matter, DALI by OpenAI, the setup of DALI, let's say, and Clip works tremendously well. I mean, this very work, although it used implicit neural sirens and clips, but the same author also sort of quoted this work where they used DALI, I mean, a rather unofficial implementation of DALI and VQ Gans, and then they fused it with clips. And I had a little bit of time to poke around with them, and the results were good. And I did not have to cherry pick some of the results in order to impress my colleagues so that they could take some interest and join me in my efforts. But I would say the results are often not cherry picked, and even if that's the case, you probably have access to the code. Maybe take that as an opportunity for an improvement. Dig into the code base and try to find the bug, because debugging machine learning models are hard enough. Now, coming to the benchmarking side of things, for generative stuff, FID, inception score, these things tend to give you a quantitative measurement of how well things are getting generated. But I'm more of a qualitative guy. I don't like to believe in numbers even when your qualitative performances are not that good enough. But on the contrary, VQ GANs seem to be producing pretty well, images that are really, really great in different aspects. Like their textures feel real, their patterns feel real, their pixel coordinate correspondence feels real. So yeah, I'll really have to see some of the examples that you are referring to, and maybe yeah, take things from there.
Okay, so there's a different question, like training these GANs are really difficult with devices that we have on our hands. So is there any way to decrease the training time, or increase the training efficiency of GANs?
I would say some, because first we need to really analyze why these GANs are hard to train. First and foremost, by their design, by
Uh, I guess he is facing a problem because of the storm.
and I'm sorry about that. So let me start from where we had left off. So we were discussing about the difficulty that we face in training GANs. I'm going to share my screen first. Yeah, Takshak'22. Let's start. Yeah. So yeah, so already optimization objective wise, GANs are pretty notorious to train. We all know that. But there are other things, like your model is too deep to be trained on a collab free GPU or a Kaggle TPU, or your data sets are extremely large to be trained on a single collab GPU. In those cases, either take smaller versions of the model, reduce their complexity, or deal with toy data sets, or reduce both of the things, like take a subsample of the original dataset on which you would like to try your ideas, and also reduce the complexity of the model, and then try popping up or try training that model. And if you are already sure that you will get good results if you scale these things up, then probably apply for things like TensorFlow research credits, because TPU research credits. And if you just Google for TRC Google, then you should be able to get it. So there's this TPU research cloud offered by the Google team, wherein if your project is research focused and if you have something interesting to work on, then you get free access to cloud TPUs, and hopefully by that your computation needs will be catered to.
Uh,
And yeah, go ahead.
there's again a similar question. What are some of the challenges faced while generating new datasets using GANs, and if it can serve the purpose of increasing the data available for training?
That's a very good question. I mean, I have personally used GANs in order to increase the size of the dataset. And believe it or not, for POCs or MVPs, when you uh, may not have a large and comprehensive dataset to train your network on, it's always a good idea to try to train a generative adversarial network, or even fine tune a pre-trained generative adversarial network on your limited dataset, and try generating try generating some synthetic examples. But as this paper shows, alias free generative adversarial networks, when you do that, often there's this inconsistency of pixel coordinate correspondence, which tend to make them look very brittle with respect to the original training examples. Now this paper seems to have already solved that. Now this is very recent, as you can see, 15th July, not very old, I would say, compared to the number of papers that we get to see in the deep learning literature. So I'll leave you folks with a link to this paper, and it's worth taking a look into this paper and see how this paper addresses the problem. Yep, that's all about the question.
Yeah, I think we can carry on with paper.
Cool. All right, now coming to the third trend on self-supervised learning. Now, how could I have missed self-supervised learning in 2021? Jokes apart, let's start. Now, let's first discuss what's at stake with supervised learning, because for NLP, I understand, language modeling, be it causal language modeling, be it masked language modeling, all of these are self-supervised learning tasks at their very core. But so far, at least till 2019, the domain of computer vision has only benefited, I mean, at least as far as transfer learning is concerned, has only benefited from large scale supervised pre-training objectives, right? But there are some things at stake with that. Humongous amount of labeled data to push performance, as we can see from many different papers, like exploring the limits of weekly supervised pre-training from Facebook. Then there's this paper called Big Transfer, where they used billions of labeled examples in order to push the transfer performance of the different models. And labeled data, as you all may already know, is costly to prepare and can be biased as well, right? Because it's up to the annotators or the labelers how they are perceiving a given image. And length of training time is very high with such large data regimes, and you can get an idea of how deep and how large this training schedules can get with these two figures that I have presented, and how complex these models can become. And by complex, I essentially mean the number of parameters and their flop counts. And by flop, I mean floating point operations. So these two are, in my opinion, the main difficulties of dealing with supervised pre-training objectives, especially in computer vision. Now, learning with unlabeled data, what's the notion? Well, it's really asking your model to be invariant to different views that are coming from the same image, right? On the left hand side, we can see this cute little dog, and on the right hand side we see two different variants of this dog. one where the pixel intensities have been slightly modified, and we have taken a random crop. And on the bottom one, we again are taking a random crop, and then we are introducing color distortions, right? Now, what happens if we ask a convolutional neural network to learn that these two different variants of the same image are actually the same, right? Now, you probably have heard about things like Siamese networks, which kind of do the same thing, but we have clever ways these days. And that's all kind of self-supervised learning is, at least in computer vision. There are other aspects, of course, but designing that pre-training objective is crucial. And this particular setup tends to work exceptionally and extremely well. Now, some other points. Intuitively, so what's the intuition behind asking this to your model, right? So intuitively, the model learns the content that makes two images visually different. That is, what is that particular content that makes an image of a cat and an image of a mountain truly different? That is one of the primary intuitions behind this idea. And preparing unlabeled dataset is, of course, way cheaper. In some of the cases, the unlabeled dataset
Yeah.
I'm audible, right? So which parts I missed out on?
We were last discussing about similarity, and the Stephen is that Siamese was good enough, but yeah, there are different flavors. Can carry from there.
Cool. So uh, again, taking a step back. So we are asking our model to be. Oh,
Excuse me, sir. Yeah, yeah.
I haven't shared my screen. I can realize that. Okay, cool. I'm sorry, my internet is acting weirdly, but yeah, it is what it is. So in the case of learning with unlabeled data, we are asking our model to be as invariant as possible to different views of the same image, right? Now, let me go back to the original example. So here we have this image of a cute little dog. And on the right hand side, we first see a randomly cropped version of the same image, and its brightness has been slightly tinkered with. And on the bottom hand, we see another randomly cropped version of the image where we have introduced some color distortion. Now, to human eyes, we can immediately say that these two versions are coming from the same image. But how do we make a computer understand this, right? Now, that is, in fact, when we are asking our model to be invariant in terms of its inference decisions to different views that are coming from the same image, right? Now, there are other pre-training objectives as well, but this particular pre-training objective seems to be working exceptionally well. So, as you probably have already heard about Siamese settings of neural networks, which operate on two different pairs of inputs. That is roughly the idea, but now we have clever ways of achieving this kind of objective. Now, what's the intuition behind asking this question to a model? And intuitively, the model really learns the content that makes two images visually different, right? For example, what differentiates the an image of a cat and an image of a mountain? Now, when we are really aware of that differentiating content, we are able to exploit the discriminative features in a manner. And as you have probably already guessed, this is exactly why self-supervised models tend to have some decent amount of transfer performance on downstream tasks like image classification, object detection, and so on. And as we will see the results in a moment. And of course, preparing unlabeled data set is way cheaper. And of course, unlabeled data in medical imaging is still not that cheaper. But roughly you get the idea that preparing unlabeled dataset does not include that separate pipeline of gathering annotators and domain experts to, get a few billion examples, if not in millions. Now, how effective is this approach? You are probably asking this question for a while now. Almost as good as supervised learning, but sometimes even better, as we will see. Now, here we see an example where it's almost as good as the supervised counterparts, and the blue lines denote the self-supervised models. On the middle, we see self-supervised vision models are performing better than their supervised counterparts. And on the right-hand side, we see them to be way more label efficient. And by label efficiency, I mean what happens when you do not have a lot of labeled examples, right? And it's a known phenomena that supervised pre-training do not work that well when we do not have access to a lot of labels. Even when you have trained a pretty well model with supervised pre-training, and then you have probably fine-tuned that model on your own dataset. There also, if you have extremely low labeled samples in your own custom dataset, then also the transfer performance might not be that well. In those regimes also, self-supervised models tend to transfer way better than their supervised counterparts, as we can see on the right hand side. Now, is it just for image classification? Because image classification is still easy, and at the same time it's still pretty practically relevant. Actually, no. Self-supervised models tend to transfer pretty well for detection and segmentation tasks as well. And as we can see on the last row, for segmentation, it's actually beating its supervised counterparts, right? Now, I hope it was convincing enough for you to start looking into some of the self-supervised models, if you are into representation learning for that matter. Okay. Now, any questions?
Yeah, like in many of the forums, like I have seen questions being raised on the bias that is introduced by the self-supervised learning, and even in some of them, questions like compared. I mean, self-supervised learning are even compared with as in a simulation made by a computer and something. So is there any I mean, I didn't find any literature denying or even establishing this fact, but yeah, there are actually some questions that are unanswered in this forum, like are these biases even diminished by the datasets that we have prepared?
Well, this particular work on Sear from Facebook tends to claim that they have downloaded 2 billion random images from the internet, and then they have trained a self-supervised model, and which seems to be having pretty well transfer performance, which also I present in the presentation. But as you mentioned, the issue on bias, well, not all the images, at least a majority of the images that we see on the internet are not random. I mean, most of the images are quite centrally oriented, and when we take images by our mobile cameras or other cameras, let's say, and when we upload them to the internet, those images are not really random per se. But this work tends to be tends to have already broken some grounds on seeing if self-supervised learning can be trained using a couple of billions of random images crawled from the public internet, and it seems to be performing well. So yeah, and I can leave this link in the chat in case you want to study it further.
Yeah, that answer I think we can move on.
But yeah, I mean, that implicit bias will always be there no matter what dataset you are using, because it's ultimately down to the dataset creators, right? It's not being created in a sort of decentralized fashion where everyone has access to on what everyone's operating with, and not everyone has access to the computation as well as the state of the system they are operating with. So it's really a hard thing to do, but maybe an interesting research direction to pursue. So yeah. And there are some challenges into self-supervised learning. Even in 2021, self-supervised learning requires a very large data regime to perform well for real-world tasks such as image classification and image segmentation. But as you can imagine, gathering unlabeled examples for most of the domains is not cheaper compared to putting together a labeled dataset. And contrastive self-supervised learning is still computationally expensive, right? I mean, things like SimClear, they are contrastive self-supervised learning techniques, and they are pretty computationally expensive. They, in order to work well, they need to be trained with extremely large batch sizes because they do not have any idea of difficult negative pairs, so-called. And I think that's it about the self-supervised learning trend. And as always, I am leaving you with a number of good reads that I have found to be extremely beneficial for my own supplementary learning, I would say. Now, yeah. Now, coming to the next trend, and this is the pre-final trend, that is the use of transformers and self-attention in for solving image recognition problems. Now, I'm really a sucker for good paper titles, and this paper title seems to be one of those. An image is worth 16 cross 16 words. How poetic and philosophic that might be. It's a little meme content for you folks. I really like cool paper titles. I can't help it. Now, yeah, attention helps. Now let's formulate some basis on transformers and self-attention. Attention helps a network learn to align important contexts that is present inside the input data by quantifying pairwise entity interactions. Like imagine, taking a sentence and then consider all the different words present in that sentence, and then consider finding a context in which you already know how each word is related to all the other words present inside that sentence. Won't that be helpful? Won't that be immediately helpful for you to infer what's likely going on? And as it stands out, this particular formation applies to all modalities of data, no matter if it's vision data, no matter if it's speech data, and so on. And this is exactly what is meant by quantifying pairwise entity interactions. Of course, there are all forms of linear self-attention and other cross-attention models as well. And as you can probably imagine, if we take pairwise entities, the computation becomes a quadratic function. And for real life purposes, quadratic things can blow up your memory, can blow up your space requirements, and so on. But that's not the point. The point is the ability to quantify pairwise entity interactions by means of a few simple equations just from the input data, and infusing some sort of context as to how the different elements present inside the input data are related. Now, here's a visual. We see a man riding, snowboarding, not snowboarding, surfing. Sorry, I'm sorry. I got a bit little tilted there. Now we can see a man is surfing on the sea, and then on the right hand side we see a caption that has been predicted by an image captioning model. And at the same time, we are also able to see an attention map as to find out how different parts of the images are related to the different parts of the caption, and how they're sort of gelling together in a coherent manner, I would say. Now, that is sort of a visual way to go about attention. I'm sure you have seen different visualizations, but I like this one a lot. Okay. Now, the idea of attention has been there in computer vision in many forms like GC blocks, global context blocks, squeeze and excitation networks that dealt with channel attention. There's other form of attention in computer vision as well, like spatial attention, but their gains have been pretty marginal. If you add AC blocks, squeeze and excitation blocks to a ResNet, their gains would still be very marginal. Now, of course, interpretation wise, you may get better results, but we also care about the top line metrics like top 5 and top 1 accuracy, right? Because that's important. Of course, coming to transformers are again a very deep stack of different self-attention blocks, and in literature we also refer to them as multi-head self-attention blocks, and they form the foundation of transformers. Now it's really out of scope for me to uh, talk more about transformers, but I'll leave you to it. Now, coming to the pros of using these setups is lesser inductive priors, and hence can be thought of as a general computation primitive for different learning tasks. As you can imagine, in convolutions, we are sort of infusing that inductive prior of locality already, whereas in transformers, we do not have such well-informed inductive priors, right? And hence, we are getting to see many research papers that are coming out of the large organizations such as Google, Facebook, which tend to throw large data samples at transformers, and they are presenting exceptionally well results. And this is exactly why the research community is so excited about trying out transformers in all sorts of different ways, because they do not require hand designed or manually engineered inductive priors such as convolutions, but they still yield quite a good performance. And parameter efficiency with performance gains, and this is a table that will convince you that vision transformers are way more efficient than their convolutional neural network counterparts, and at the same time they give you performance boosts as well. Now here are some cons. The importance of large data regimes is paramount during pre-training, because transformers do not have well-defined inductive priors such as CNNs. But there have been recent improvements that seem to be getting away with this problem, and specifically they have demonstrated good performance on the seminal ImageNet 1K dataset without using any external data. And here are some examples. But it's still possible to outperform the vanilla ResNets without having to pre-train on a larger data set, and without having to use strong data augmentation techniques. And these results are for ImageNet 1K. And I have also sort of mentioned these two papers that show you how you can get away with that large data regime requirement for transformers, and they present it in a very systematic manner. So I highly encourage you folks to check it out. Now, when self-attention is combined with CNNs, you might be immediately asking, hey, what happens if I can just incorporate self-attention within convolutional neural networks? Well, you can certainly do that. And believe it or not, they establish pretty strong baselines, such as botnet. This is roughly the architecture on the left-hand side of bottleneck transformers, wherein they're just replacing the final residual bottleneck with a bottleneck that is based on the transformer blocks, right? And if you just do that, the vanilla ResNet architecture, gets outperformed. And on the right-hand side, you can see some of the results. Now, in the interest of time, let me move on, but you will still have some minutes to ask me questions. And as it turns out that if we systematically fuse relative self-attention with convolutions, if we can do that, then we can actually outperform vision transformers or that family that marries self-attention and convolutions in some way. And this is roughly the architecture of quote nets. It's still a recent architecture proposed by the Google Brain team. And as you can see, the results are pretty convincing. A convolutional neural net infused with position-aware self-attention, outperforming vision transformers all the way. And they do not even require pre-training on JFT 300 million dataset. This code net was pre-trained on the ImageNet 21K dataset. And at the same time, it's still able to match the performance of a vision transformer that was pre-trained on a much larger dataset. But that is not the point. We are kind of convinced by the results of CodeNet, but at the same time, of course, there's this, influence of using convolutions. So we are probably not bidding adieu to convolutions anytime soon, but it's, so that was one of my objectives of presenting about CodeNet. Okay, here are some, fun links for you to try vision transformers, and definitely explore vision transformers. They're fun. And I have also presented a couple of implementation, links that show you how you can implement a vision transformer within 300 lines of code in Keras. And there are, there's this entire repository of different vision transformer models on TensorFlow Hub. So definitely check these links out if transformers are something that interests you in the context of computer vision. Now, this is my final trend, but before that, I would like to see if there are any questions.
I mean, there have been articles, LSTMs are long dead. I mean, are dead, live long transformers. So like, so after how many? I mean, according to you, after how many years can we like say the same about CNNs? Because you just now said that about inductive biases and the locality of CNNs that are well removed by the global attention that's provided by transformers. So yeah, I mean, people can see that coming soon, but how soon is that? Like CNNs are considered redundant like LSTMs.
Great question. Again, I think it's too subjective to comment on this, but I will leave you with a few different use cases. So first point is, given that fully connected networks having a structure of multi-layer perceptrons are already performing good enough with respect to convolutions and even self-attention and transformers, it's still hard for even a research scientist to give you an affirmative answer. But as far as practical deployment is concerned, there are other things you need to take into consideration, like how interpretable are these models, and then if you are deploying things on mobile phones, the vanilla convolutions tend to be performing extremely well. I mean, they are better performing than transformer-based networks. So the arrangement of regular vanilla good old convolutions are particularly well suited for mobile GPU hardware. So that is one case. But at the same time, again, there's this concept of technical debt. How well is the team equipped to deal with the nuances and idiosyncrasies of transformers? So that is definitely one of the questions that all machine learning engineering teams are asking these days. But from a research standpoint, I do not really know, because if we are able to get this kind of performance benefits from fusing self-attention and convolutions in meaningful manner, I'm still not convinced that vision transformers or, let's say, multi-layer perceptrons are going to be taking away the place of convolutional neural networks. So yeah, I probably not a very comprehensive and to the point answer, but I can't help shake this feeling. Yeah. Okay, now this is the final trend. I'm not going to be boring you folks with any more glory details of things like vision transformers, because ultimately this is a Sunday. You folks are entitled to watch some things on Netflix or Amazon Prime or whatever. But yeah, this is my final trend, and I hope this is of some usefulness. So in this trend, I would like to introduce the concept of robust vision models. Now, before we proceed, robustness in the context of computer vision has got many different facets, right? But we will be considering only a few of them. Now, when I mention that, hey, my vision model is extremely robust, it might very well be the case that it's still a brittle one when it's being met with adversarial perturbations, but it's still robust enough to perform well on images that have common corruptions. So robustness can have many facets. As I was mentioning, perturbations. So deep models are brittle to imperceptible changes in input data, as you probably have seen in this pig image, wherein to humanize both of the images are of pigs. But it stands out that if we introduce this random but learned perturbation vector to the left sweet little pig, then it gets classified as an airliner by a neural network. And these are some of the intriguing properties of neural networks, as you may like. Now, coming to the perturbations, as I was mentioning, deep models are extremely brittle to imperceptible changes in input data. And this has got a pretty stern implication as far as practical deployments are concerned. Imagine if a pedestrian gets predicted as an empty road. If you have deployed a model in a self-driving car, and in real time it has to predict different objects that it is perceiving in its camera from its camera feed. And imagine if a pedestrian gets predicted as an empty road, what happens then, right? So the practical implications of adversarial perturbations are paramount, and it directly concerns the security aspect of machine learning models. Corruptions, then there comes all sorts of corruptions, right? And deep models can easily latch into high frequency artifacts that get introduced when you try to corrupt a natural scene image. And of course, this high frequency artifacts can make them brittle. And by common corruptions, I essentially mean things like blur, contrast, zoom, and so on. And on the left hand side, you can see some examples where we have introduced salt pepper noise on some of the examples from the CIFAR 10 dataset. Not CIFAR 10, these are coming from the ImageNet 1K dataset. And here are some more examples of corruptions. It's probably the Gaussian blur. And here are some more examples. So if we introduce this common corruptions to natural images, then also the vision models can fail. Now, there's this another kind of robustness, that is the ability to perform well on out of distribution data. And out of distribution data can be in two kinds, where we have shifted the domain, but the labels are still intact. And on the left hand side, we can see some images from the ImageNet 1K dataset. But on the right hand side, we see cartoonized and other renditions of similar classes taken from the ImageNet 1K dataset. And we want our models to perform consistently with respect to its training, right? If our model is performing well on the examples from the ImageNet 1K family, then it should be performing well on similar looking examples, because to humanize this, all these examples are similar looking, right? But we of course can understand that probably their textures are different. But if your textures are different, that does not change the class of the image that we are seeing, right? And there's this another kind where we deal with anomalous data points. So let's say you have trained your model on a particular set of class, and when we are presenting an image from a different class that was not presented in the original label set of the training data, we would want our model to be as uncertain as possible, right? it should be predicting with low confidence. It should be informing the user that, hey, I'm not that much confident on the image that you have given me to predict. So it should be reflected in its predictions. And as Balaji Lakshminarayanan has said in the New RIPS 2020 workshop, all models are wrong. He basically extended the famous quote from George Box. All models are wrong, definitely. But models that know when they are wrong are useful. And by when, he was essentially referring to the phenomena where your model is informing you about that, hey, these images are probably faulty. I'm not feeling very confident about predicting them. So that's the idea, roughly. Now, for further versions, here are some solutions. Adversarial training seems to be working tremendously well, but again, there can be different types of adversarial attacks. And if you train your network on one kind of adversarial attack, it may not transfer well on the other adversarial attacks as well. And it's kind of analogous to, yeah, go ahead.
Yeah, like Sayak, I would like request to please make can we wrap things in like 10 minutes?
Yeah, actually we can wrap it up within 5 minutes. I only have 3 more slides to present.
Thank you. Yeah, sure.
Yeah, I do care about the time. So yeah. So adversarial training is kind of analogous to Byzantine fault tolerance, if you like. If you are already familiar with distributed systems, I hope you already know what Byzantine fault tolerance is. And here's one example that sort of extend the idea of introducing adversarial training in the context of pre-training itself. And as it turns out, that adversarial examples do improve image recognition. Now, coming to other things like denoise smoothing and neural structured learning, these are all extensions of, defending your neural networks against adversarial examples, because by now I hope you have realized that their practical implications are quite brutal and quite stern. For corruptions, consistency regulation seems to perform tremendously well, and the idea there is this rationale of, we want our models to be consistent and noised inputs, right? We don't want our model to break when it's meeting with slight corruptions, because it's not practical enough. Noisy student training, and yeah, of course I'm going to be mentioning noisy student training because it extends the idea of consistency regulation beautifully. And yeah, all of this words, extend the idea of consistency regulation, and then push the state of the art. And here's some more links to the solutions. Not solutions, these are not foolproof solutions, but they provide you with enough context to get your feet wet. So yeah, I think that's about it. Now, if you have any questions, I'm happy to take them, or else we can take them offline. You can always email me and ask your questions, but I will definitely leave this link so that you can access it if it's needed. So yeah, and I'm done. I don't have anything else.
I don't think we have a question. Okay. But yeah, really thankful and happy. I mean, we are really I can't even put a word to it. Yeah, that was really interesting, and thank you. We couldn't have a squirrel photo to have you say thank you, but yeah, we're very happy to have you, and yeah, thank you to all the participants and to join us. I mean, I have a personal experience with telling Sayak a couple of times, so I would suggest anyone who has a question about anything starting from OpenSys to computer vision can always mail him up, and he would get back as soon as he can. So yeah, that's the best thing I like about him. So yeah, thank you, Sayak.
Yeah, I'm happy to be here, and as you mentioned, feel